like last time. And so that was a real life example of reverberations. If you study AGN, then you can use the echo of light. Um, yep, like that one to kind of like gauge your distance or measure like the slope of the equation disk or everything that you want to do. So yeah, that's kind of real life example of astronomy in the working. Let's let's make the best of the mistake that we have. So again, welcome everyone to the second day of the workshop. Today we have Dr. Samaphon Tinyanon, who will be telling us about this first session will be astrometry, right, and photometry. Okay, so let's Dr. Samaphon, please take it away.
All right. Hello and good morning, everyone. As Bright Kitapat introduced me, my name is Gao Samafontinyanon. I'm researcher here working at NARIT on transient astronomy. So I'm interested in massive stars that blow up in the night sky and outshine this host galaxy. And we will get to look at some of that later on today. But for this morning section, my job is to tell you what to do with the images that you made yesterday and also astronomical images in general. So yesterday we looked through the raw data files and we apply a bunch of corrections to make them as true to light as possible. And now, now that you have an image that is quote unquote science ready, you can make measurement from it. So we will look at the two main ways that astronomers look at images today. So the goals for this session for me is one, you will learn about absolute astrometry. What this means is that astro is star and metry is like measurement. So we are measuring stars, and what this means is measuring the positions of stars in your image. And by absolute astrometry, what I mean is that you want to measure, you want to convert the XY position on your image to the real coordinate on the sky. And we will talk about that in a little bit. We will then switch gear. We will not spend too much time on astrometry. It is complicated, but thankfully there's a software package that makes things really easy. So we'll see that in a bit. Then I will spend most of our time looking at photometry, and this is the measurement of the brightness of the stars, all the point sources, galaxies, whatever that we have in it. And this is quite difficult in the sense that just the measurement, the technical part of it is not very difficult, but you need quite a lot of physical background to understand what you are trying to measure. So we will spend some time today, this morning, looking at all the relevant radiative quantities, what physically we are trying to measure in these images. We will then learn two techniques to do photometry to actually measure how bright things are from the images. One is called aperture photometry and one is ESF photometry. So we will see what those words mean. And then after we have this measurement, the unit is still in the counts or in ADU or whatever unit provided by the image that you have. We will talk about how to convert those fake units from your camera to the real unit, which is these radiative quantities that we will talk about earlier. Yeah, and that should be kind of a broad scope of what we're trying to aim today. There will be kind of a small break in the middle, so don't worry that you have to sit through an hour and have it. All right, so let's get started. So first thing first, one of the very important properties of an image is how big each pixel is compared to the sky, right? And this is a number that we call pixel scale. In the olden days, before the CCD, the number that astronomers use is called place scale, and this is essentially the angular size on sky, usually in arcsecond per some linear distance on the focal plane. And this is because back in the olden days, there are actual photographic plates of film that is put at the focal plane to get exposed to the night sky and produce image that you can see on this physical object. And because of that, you can like make measurements using a ruler to see, you know, how many millimeters stars are apart on this photographic plate. And because of that, we have some number called place scale. So it's like something like arcsecond per millimeter. Now we have pixels, so it's a little bit different. So instead of measuring things in millimeter, we measure it in how many pixels things are apart on our image. So say if two stars are 25 pixels apart from my image, how really far apart they are on the sky. To measure this number, you need to know two things. One is the focal length of your telescope. Usually you can look this up. Most observatories will have this information listed. If not, usually they will give you the diameter of the primary mirror of the telescope and the F ratio. And the focal length is just diameter times F ratio. And this is the fundamental property of any optical system. And this number that you need is the effective focal length. So this is the focal length that your instrument sees at the focal plane. Sometimes telescopes have different mirrors and lenses, and all of them have different focal lengths. But the number we care about is the combined focal length of the whole system. And usually this is the only number that they tell you anyway. The next number that you need is how big your pixel is. And to know this, again, you can go back to your to the manufacturer website, and usually they will tell you what the physical size of your pixels on the CCD is. This number is usually roughly around 10 micron on like astronomical CCD. Things like, you know, CMOS chip on your phone camera is much smaller, usually in order of a few microns. That's also why pixels in these astronomical cameras are a lot more effective. So for example, the TRT, the telescope that we use for the images we looked at yesterday, it's a 0.7 meter telescope in diameter, and the focal length is 45-40 millimeter. The camera we use is this Icon M CCD, have pretty standard 13 micron pixels, and the pixel scale is just the size of the pixel divided by the focal length. That's all. And here, so that's the calculation. The result, because you have some length divided by a length, you get a unitless quantity. And when you have a degree that is, when you have an angle that is unitless, the unit is radian. And if you haven't heard of it, should look it up. And you can convert this angle in radian into degrees or arcsecond, and in this case, it's 0.59 arcsecond per pixel. So now we can do something called relative astrometry, which just means measuring distance between different stars on our image. You can now bring your image up and try to measure how big that galaxy is. You can try to measure how big the field of view is. You can try to measure distance between any two stars in your image. However, if you take this image and try to go tell your friend, oh, look, there's a supernova here, point here. How do you tell them, right? Because the information you have so far is just the different distances between things that you have on your image. How do you place this image on the night sky, and you can tell other astronomers, go look there. So to do that, we need absolute astrometry. We need to be able to tell them where exactly on sky it is. So yes, that is the mapping from pixel to sky coordinates, and they will show up in DS9. That's very convenient numbers. Before we go on, let me ask if anyone here is familiar with celestial coordinates, right? Ascension, declination. If you can, if you confusion, but so I can go through it quickly. It's essentially just like latitude, longitude on Earth. You know, it's the same thing. You're trying to find location on a sphere. So the one that is most relevant to observational astronomy is called equatorial system. We just extend our equator and our pole out into the sky, and then the latitude is called declination. This is the degree from the equator. And then the longitude is called right ascension. And there's one 0 point on Earth is like somewhere in Greenwich. On the sky, this is vernal equinox, where the sun crosses back into when the sun traveling through the ecliptic cross back into the northern hemisphere. Let's see. RA is a little bit weird. If you have noticed, it's measured in hours. Sometimes it can also be measured in degrees. And it is measured in hours because RA is the direction in which stars travel when the Earth rotates. And if you wait an hour and the Earth rotates 15 degrees, so the stars that are at the same place you were looking at before are now with RA 1 hour more than the stars that used to be there. So it's quite a convenient unit to use. And when you're planning the night, you can also look things up easily. You can know roughly when things will set based on what the right ascension is. So yeah, that's just the numbers that we use. One word of warning is that coordinates are always given with the epoch. And the reason is because this vernal equinox point that I mentioned, that is not static, right? We know about the Earth precession of the Earth rotational axis. And this is why like North Star 20,000 years ago was different from the North Star here. And because of the same reason, these RA and DEC coordinates also change with time. And the current epoch we're using is 2000. We are marching forward to 2050, which is a horrifying thing to think about. But if you have a target list catalog or anything older than 2000, beware, because the coordinates on there could be from 1950, and they're very different. Depending on where you are on the sky, if you take an image, using this coordinate, thinking that you're using J2000, then you will not even be in the same field of view at all. And say this from experience, and I'm sure like a lot of people who have planned observations before have this like horrifying thought in mind. Most facilities these days really like help you verify that like whatever you put in is the correct thing. There are also a couple other systems that we use in addition to equatorial system. There's a ecliptic that I mentioned earlier. This is just based on the plane of the solar system. Well, to be exact, the Earth orbital plane around the sun, and this is relevant for solar system science. There's also a galactic system that uses Milky Way disk, and this is again relevant for galactic and extragalactic science. You want to look away from the plane of the galaxy to be able to see deep into the universe. So we can look those up. Now, the old school way of doing absolute astrometry is essentially a problem of linear algebra, right? You have a bunch of stars for which you already know the coordinate. And this is probably, this could be from some kind of catalog or from some databases that you can look up. And hopefully you know roughly where you were pointing at when you took your data, so you can try to look up stars in that region of sky that already have known coordinates. And So you can make a list of some XY coordinates. This is just the pixel coordinates of those stars. You know the array index, and there are a bunch of software packages that can help you produce this transformation matrix that you can apply to XY to convert that to array index. Kind of the most classic one is in IRAF. If you haven't heard IRAF or don't know IRAF yet, our goal with this workshop is to make sure that you don't have to deal with that. but but if you unfortunately have learned IRAF, which is also, you know, very useful software packages from like the 80s that work really well, but it's such a thing. There's a package in there called GeoMap and GeoTrans that can do this work for you. More modern, preferably. We also have AstroPy package called this fit WCS point. You can look it up later. We will not have to use this, fortunately. And the reason is because there's a tool called astrometry.net. And there was a True to Life a website that you can go to, upload any astronomical image. Doesn't matter. It can be fit files, it can be a phone image, it can be like JPEG from amateur astronomy camera, and then it will do some magic, and we will talk about the magic in a bit. And then figure out where you are on the sky for you. It's quite amazing. And in this kind of example, you know, somebody I don't know who, I just screen capped this from the website, uploaded a picture of this fireworks galaxy, and astronomy.net figure it out for them. That's the object they're looking at. So it's very useful. The way it works is quite fascinating. It's based on pattern matching with these kind of polygons on the sky. So when you if you try to install astrometry.net on your own computer, what you have to do is you have to download like gigabytes upon gigabytes of all these polygons that it uses. And essentially these are kind of polygons with 3 or more sites that are unique on the sky based on just like, you know, star patterns. So what astrometry.net does is that it runs some kind of source extraction to find all these stars, and then try to match these sources with their huge catalog of polygons on the sky. And it will take a long time, but it will eventually find it. Now, to make it to make this a much faster process, you can give it initial array index, like roughly where you were on the sky. And also if you can give it how big this image is, it can also know to look at only polygons in the appropriate sizes. And if you give it all these help, then the process can take not even a second. But if you give it completely blind, just throw it a picture, then that can take several minutes. There's also a command line option if you install this thing on your computer. It is not the most difficult thing to install, especially if you have a Linux. It's very simple, but Mac OS is a little bit iffy, and Windows, just forget about it. But yeah, if you can do this, then all the these additional parameters can be given a lot easier. So it does this magic, then somehow coordinates array index pop up in your fits image. How does that happen? This is done by using something called the World Coordinate System, or WCS. You will hear this quite a lot if you deal with astronomical images. And this is a pretty clever way to do it, because you could theoretically have just another array that have all array index at every pixel, but that would not be data efficient, right? You will, like double the size of your image for no good reason. And the reason is because you can save the same information using only 8 numbers, and these are the capitalized names. These are things that are in the fits header. If you go look at your fits header, you will see all these keywords. There's a reference pixel, which pixel you're using as reference, CR pix 1 and 2. There's a reference coordinate. What are the R index at that pixel? That's the R val 1 and 2. And then there's a transformation matrix, which is a 4-element matrix. And you can convert to R index, which is alpha and delta, using that equation. And this is just useful to keep in mind when you deal with images. This is how this information gets stored. Again, in the header like that. And when you're using Python, you can read it with AstroPy WCS package. Very nice. All right, so quick summary for astrometry. Relative astrometry is when we are measuring where stars are in relative to others on the image. And the only thing you need to know is the size of your pixel. And absolute astrometry is where you try to say what RA index that star is. I think we can have a really quick and brief break. Don't know how brief this is going to be, but this is a mini exercise. So what I want you to do is maybe work with your group, because we don't want to, crash their server. But if you go to nova.astrometry.net and try to upload the image that you worked on yesterday, just one band, and try to see what the results are. I'll give you 10 minutes. And the big hint is use the advanced setting drop down, so you can set the scale to tiny, which is the size of our image, and also set the RA index. And you can use the initial guesses from the fit header. This should not take long, but let's see. If you have any questions, raise your hand and I can try to help. And even if you don't have the fully processed image, this will work on the raw image. Yeah, if anyone has questions. If you can access it on your computer, I think the server is blocking us. So find someone with a working copy and work with them. Anyone need help? Anyone is done? Yeah. I think yeah, too many people have to be spoken. And this is kind of typical for like astronomical web infrastructure. It's there are not too many astronomers, so the webs are built to accommodate like 10. All right, so we have a couple of people who successfully run this. If you run into a server issue, you can go look at their screen. Who else have a working result? I got one here if you want to look. All right, so in the interest of time, let's move on. A few people successfully run it, and I'm sorry that I didn't expect the website to crash for more than 10 people. And I think this could be the hotel internet as well. Somebody successfully connected to their phone and got it to work. But sorry for that. I will post some like result page on the slide when before I share it. All right, so that's astrometry, and please believe me, astrometry.net really makes like all our life much easier, especially for like a large scale imaging survey. Astrometry used to be the most painful part because it's extremely manual. But now everyone does have astrometry.net running on their computer and just feed it through. So let's talk photometry. See, some people just showed up, so they missed the easy part, and now they're going to be pelted by by photometry section. All right, so photometry is the science of measuring light, right? Similar to astrometry, the photo is light and metry is measurement. So this is how we measure light in astronomy. And to introduce this topic properly, I have to tell you about all these fun and annoying physical terminology, which is using common words to specifically identify different physical numbers. So first thing is luminosity. The luminosity is just power. This is just energy output of any kind of object per unit time. This is just how many joules or how many earths of energy you get out per unit time. This is luminosity, same as power. And this is kind of like a, one of the more fundamental quantities from each astronomical object. Like if you can put a net around the sun and collect all of the light coming out, this is what you get is the luminosity. And obviously we cannot do that because we are sitting here on a tiny little blue dot, very far away from all these astronomical sources. So what we get to measure instead is flux, and this is luminosity or power per unit area. And this is simply luminosity divided by the surface area of the sphere with the radius equal to the distance between the source to us. And this is simply because you get that luminosity, you assume that it's isotropic, and this is the use assumption is that the light goes equally in all directions. So you just divide it by 4 pi d squared, where d is the distance. And this is called the inverse square law. And what that means is that if you go twice the distance away from a source, the amount of light goes down by a factor of 4. And this is simply because of the nature of the spreading out and how the surface area of the sphere evolves with distance. The fun thing is that we can actually use this to measure sources with no luminosity. So if we have something with no luminosity, we can use that to measure distance. And this is the method called the standard candle. No time to talk about that. today, but that's a terminology you can look up, and you can also talk to me. But more complication. Even when we are sitting here at Earth with our tiny little telescope, maybe half a meter, maybe 10 meter, we still do not observe all of the light that is emitted. And that's not just the spreading out part, but it's also because this light is emitted in many different wavelengths. And our device is sensitive to a range of wavelengths, as we saw yesterday. Our telescope sometimes maybe not sensitive to things like X-ray emission at all. And most of the time, it is really difficult to gather all the resources to collect light all the way from gamma ray to radio. So usually as for astronomer, we only get access to just a sliver of the electromagnetic spectrum at a time. And because of that, we have to make some kind of quantity that reflects this unfortunate nature that we simply do not know everything. And this is why we measure something called specific flux or monochromatic flux. And what this is the flux measurement that is also per unit wavelength or per unit frequency. And when you have this quantity, you can measure it at every single small bin of wavelength. And this is really what we measure when we do photometry. There are two versions, as I mentioned. You can divide it by wavelength bin or divide it by frequency bin. And these two quantities are often referred to as F lambda or F nu. They're not the same and they're very different. And surprisingly, people get it wrong quite often. This is the quantity we try to measure, and you can convert between the two by that simple equation. Lambda times F lambda equals to nu times F nu. And as a reminder, for any light, wavelength times, wavelength times frequency is the speed of the wave. In this case, it's the speed of light. A side note, if you're so physically inclined, there's another granddaddy of all the quantities called intensity or specific intensity. And this is kind of like the most fundamental quantity that we use in radiative transfer. And this is the added the added detail for intensity is that it's not just per unit area of the light, but it's also per unit solid angle where it's from. And when you use specific intensity, you can specify everything that you want about a light ray. For observational astronomy, this is very similar to or physically the same as surface brightness. So say if you have a galaxy, something that is spread out and not a point source, you can measure like how bright it is per unit area on the sky. And that is kind of the same as specific intensity. If you're mathematical inclined, that's the way you convert from frequency to flux. But let's not get into it. So magnitude system, we talked about this a little bit yesterday, and so let's have a recap because it's very important and it's one of the first things you learn in astronomy, and then it's one thing that you keep using it all of the time because of this kind of a hole that we dig ourselves into. But it's very, very useful, please believe me. So Hippocrates in about 150 BC probably said that stars have 6 level of brightness from 1 to 6, 1 being the brightest and 6 being the faintest. And a story I heard that I'm not sure it's true is that the reason why it's numbered like this is because the first magnitude stars are the first one who showed up in the night sky, right? If you're like at dusk waiting for the sky to turn dark, these are the ones that showed up first, and then progressively go up to number 6 where you have to like have really dark sky and really good sight, which he probably has at 150 BC. So yeah, I think that's a justification that is satisfying to me. But because of this definition, you need 1 through 6 with magnitude 1 star being 100 times brighter than the 6th magnitude star. You can write out an equation like this, which is that the difference between the magnitude of two sources, M1 minus M2, is minus this reflects the fact that the scale is inverse, 2.5 for some reason, and then it's a logarithmic 10 of the ratio between the flux between the two sources. So what this is really telling you is that the magnitude is just kind of like a decibel, or kind of just like any other logarithmic unit, and we use this all the time in science, right? Because a lot of a lot of the time things comes in this multiplicative factors and not linear. So this is a natural unit to use. And when you have like a quick conversation with colleagues about how bright things are, try quoting a flux number, and they will like annoy them really quickly, because you have instead of like just a simple number, you can quote it like, oh, is it like 10 to the 10 to the 1 of some unit, or this is 10 to the 5th, or this is 10 to the 10, because the range is so high. But in magnitude, you say, oh, this is a 12 magnitude star, and everyone knows, oh, okay, 12 magnitude is very bright. For big telescope, you can't see with your eyes, but with any telescope, you can take an image really quickly. If you have a 10-meter telescope, maybe you don't point it at that star because it will be too bright. So it helps communication a lot. And when we make this measurement of magnitude, usually we make it in different photometric bands. So this is, again, just a recap of what we talked about yesterday. There are several standard systems that we use. Most classic set is this so-called UBVRI. You can sometimes you see them referred to as Johnson, Bessel, or Cousins filter. There are some like small differences between them, but generally it's the same. And the more popular these days, the kind of like a more modern system is from the Sloan Digital, right? The Sloan Digital Sky Survey, and it's also adopted by Pan-STARRS, by CTF, or a lot of the more modern sky surveys. And this is called UGRIC, and these are always written in lowercase. And I just want to point you to this resource. The SEO filter database is an amazing resource that have only been around for like a few years, and before that, you simply have to like go to the website of the observatory and like hope and pray that they like actually tell you what the wavelength or the actual wavelength of the filter that they use is. Right now, with this service, everything is in the same place. More glossaries, more terms. We talk about magnitude, but really when we talk about magnitude of things we see here from Earth, that is called the apparent magnitude. And that just tells you how bright things are based on observation from Earth. But how would you tell the difference between things like the sun, which is, blindingly bright, literally. But if you put the sun at the same distance at things like Betelgeuse, you can barely see it, right? Like in comparison, it's much fainter than those like supergiant stars, or like any stars in Orion are like very luminous. So how do the magnitude number that tells you kind of like the intrinsic brightness, or the like it is actually tied to luminosity of your object, is called absolute magnitude. And again, as astronomers like arbitrary things. So absolute magnitude means if you take this source and put it at 10 parsec away from Earth, how bright, like what is the magnitude of that source that we will see. So because of that, that's the definition of absolute magnitude, is that the absolute magnitude minus absolute magnitude is 5. And the extra factor of 2 here comes from the inverse square law, the d square. When you check log, it pops out. So you get 5 times log 10 of the distance of your source divided by 10 parsecs. So it's always annoying to do this calculation and have to divide by 10 parsecs and not 1 or any other unit. So that's one number, absolute magnitude. Another number that we will talk about again this afternoon is bolometric magnitude. And the real definition of bolometric magnitude is the magnitude that includes all light. So this would directly relate to the luminosity of your source. Now, of course, the problem is, as we talked about earlier, we never get to see all of the light coming out of the astronomical object. So usually we estimate this by assuming what the underlying distribution of energy looks like, and we will do this in the afternoon. And then we say, okay, in the background it looks like this. We have 3 observations. Let's fit a model to it and extrapolate and fill in the gap of the unobserved future and see what the total amount of light is. Again, yes, as I mentioned, we'll do this in the next section, so you get to actually experience the joy of fitting a model to some data. And lastly, color in observational astronomy has a precise definition. This is the difference between magnitude in 2 bands. So say if you take the magnitude in the B band subtracted by the magnitude in the V band, we call that the V minus V color. All right, so now we are sort of familiar with all the terms. Do we have any questions? Now we good. Yes.
I was just wondering what's the difference in the bolometric magnitude with surface brightness, since both of them are like total surface of light coming from objects. So I was just wondering what's the difference between bolometric magnitude and surface brightness.
Bolometric magnitude and surface brightness. Yes. So let's see. So surface brightness refers to more like the objects that you can see spread out on the sky, and it's not a point, right? So say like if you have a picture of a nebula that is spread out, looks nice. Surface brightness tells you, like, we'll get to this, but tells you how much light you get per unit. Say if you have a box of 1 by 1 arcsecond, how much light comes from that? That's surface brightness. And then bolometric magnitude, it's everything in the sense that it is all wavelength. Yeah. So bolometric is everything in the sense of it covers all of the wavelength. So say if you have a magic photon detector that can detect anything from gamma ray all the way to radio, and you use it to observe your source, that observation will give you a bolometric. And yes, I said I want to get back to the surface brightness unit because it is often quoted in magnitude per arcsecond square, which is the worst unit on the planet because if something has say 8 magnitude per arcsecond square, and you have 2 arcseconds square of it, the surface brightness is not 16, right? Because it's a magnitude. So the calculation is very, very annoying. All right, so now that we know some of these terms, let's talk about the 2 methods that I mentioned earlier of how we actually do photometry from our data. So first one is aperture photometry, and this is kind of like the most basic way you can measure light from your image. And this is just by defining some kind of aperture around your source. here, and more simply, people always use just a circle unless you have a reason not to. And you know, these reasons might be your source might be some kind of like a oblong shaped galaxy, or it can also be that your mount wasn't tracking very well that night, and then all your stars look like a blob instead of a dot. Either way, you can. It doesn't really matter what the shape is, but here, what you do is that you draw a little circle around your star, and then you take all of the pixels that are inside the circle, and you sum up all of the pixel value. And you can actually just do this in DS9 if you have DS9 installed. You can go to region, set the shape to either circle or rectangle or whatever. You draw a circle around it, and then when you click on that circle, there's a menu pops up called statistics of properties, and you can, I think it's property and then statistics, and then it will tell you what the sum of all the pixels inside of that circle is. That is as simple as that. There's no modeling, there's no assumptions going into it. And usually when you do this, you also have to take the sky background into account as subtracted. And the reason is because even after we do all the processing, all the background subtraction, during our data reduction process, the background of your astronomical image is often still not zero. And this could be due to, like residual from your subtraction process. Or you can, as often in supernova science, you have really bright galaxy behind, and then your supernova is on top of the bright galaxy. So you can rarely really subtract it out. We will talk about it, I think, in the future section this afternoon. Oh, no, maybe about like more advanced background subtraction techniques. But usually, this is kind of like the most simple way to do it, is that you draw an annulus around this photometry aperture, and then you use a flux in there to estimate how much background is behind your point source. When you do this, you get something called instrumental flux, and this is, in the unit of counts or yeah, whatever your chip gives you. Of course, this doesn't have any physical meaning, so we will have to convert that later. But for now, let's use this term instrumental flux to refer to the sum of all the pixels that you get. Now, obvious question is, how big does this circle have to be? Like, obviously you don't want something that is just right on top of your star, because that will not get all the flux. But you also don't want one that is so enormous that get contaminated by other sources and have a bunch of noise from the area with no signal. So there's a technique called a curve of growth to try to figure out what size of the aperture you should use. So this is an example that I did quickly on DS9 as promised. This is an image. You can see the star here, and I draw 3 different apertures with some background analyst far away. So the top curve labeled raw count is to demonstrate why you need to do this background subtraction, because as you increase the size of the aperture, you get more and more of this background light. And because of this, the amount of counts enclosed in the aperture just keep going up with the size of the aperture. But really, there's nothing there, right? So if you do proper background subtraction, you have an analyst, roughly how much the background is, and you subtract it out, you get the lower curve label background subtracted. And here you see that, sure, if your aperture area is really small, you barely get any flux, and that is the smallest aperture you have there. But as you increase it, you start to get more and more flux. But once you increase it so much, there's no, the flux doesn't go up anymore because you already have enclosed all of the flux in your aperture. And in the exercise that we will do right after this, you get to make a much more detailed version of this. This is a quick and dirty way to demonstrate it. Another Another thing that you do for aperture photometry is that sometimes the optimal size of the aperture that you use for different objects will be different, because bright things might have detectable flux out to a much larger radii compared to fainter things. And in that case, you might want to use different size of the aperture to do photometry for different objects. But when you do that, you have to do there's a correction called aperture correction to make sure that the measurements made from using different size of apertures can be compared with each other. And that is another thing that we'll look at using the notebook this afternoon, not this afternoon, but right after this. Now, if it's so simple, if it's so easy, it doesn't rely on any assumptions, why do we have an alternative to aperture photometry? And the reason is because there are a few scenarios where aperture photometry does not work very well or at all. The most notable is when you have a very, very crowded field. This is the image of the globular cluster. If you're familiar with globular clusters, these are collections of really, really old stars in the Milky Way halo. And the core of it can have like incredibly dense amount of stars. And you can look at this image and imagine yourself trying to put an aperture on it to measure the brightness of anything, and you can not do that without having contamination from other sources. So get one of those remote. Another reason is aperture photometry is susceptible to bad pixels and cosmic ray hit and saturation and all those image artifacts. And the reason is because it doesn't make any assumption, it doesn't make any attempt to try to mitigate those issues. So this image, it shows up a bit on the screen, but you can see there are some hot pixels here, and there's even here right on the star. So if you take an aperture around this, you will individually include the flux from this hot pixel that is not real, not from that star, into your measurement. And yes, I also say saturation on the right here. I'm showing the profile of the star. If you make a projection cut on DS9, you can see the star in one direction looks kind of like that. If you have saturation, usually what happens is that instead of the count keep going up, it will stop at the maximum value that the CCD can output, and you have this kind of a top hat shape instead. So if you do aperture photometry around this, you will by mistake think that there's not as much flux because there's some the top part is not captured by the CCD. So aperture photometry is susceptible to all these things. And because of this, and other reasons, we came up with a process called PSF photometry. And to talk about PSF photometry, I have to first tell you what a PSF is. So PSF stands for point spread function. And as the name suggests, it's the function that describes what a real point source looks like after traveling through all of your optical systems. And usually this has a functional form called a Moffett function. You can look it up what the definition is. More simpler, sometimes people just use a simple 2D Gaussian. Doesn't often do a good job, but you can play around them and try to see them after. So the process for this is you have the observation and you have some functional form called this is your PSF model. You think you know what the shape of the PSF looks like, and you try to fit that to the data. And the nice part is you can see like on the right, on the left figure here, that spike try to represent like a cosmic ray hit or a hot pixel. And you can see that because your model is smooth, it will not include that feature into your measurement. And on the right here is how PSF photometry can deal with saturation. You know, it fits to the wing of your observation, and then just ignore the top. This would also work really well. This would also work much better than aperture photometry when you have blending. So when you have a lot of sources that you cannot quite resolve, because PSF models can attempt to distinguish contribution from all these different sources. Of course, it's not always a good thing to do, PSF photometry, and that's why we don't do it for absolutely everything. One crucial use case that PSF photometry is bad for is when you require really high accuracy of photometry. And the reason is because the accuracy for PSF photometry is limited by how well that parametric function can fit the real shape of your PSF. Because, you know, all of the factors that influence the shape of the PSF, that's not really a good way to like perfectly capture all of the little features you see in a PSF. So especially for things like exoplanet transiting science, when you try to detect like sub 1% change in the starlight, they have to always use aperture photometry. And in that case, it's fine because their stars are always isolated, no blending issue. They have to make sure they don't saturate the detector. They have to make sure whatever hot pixel and cosmic ray are taken care of. But after that, you can use aperture photometry to get really high accuracy. Another issue is that the PSF also changes across the field of view. And this is a property of any optical system. Point spread function is not going to be the same in the center as it is on site. If you do photography, you know this very well because you know the lens prices go exponentially up with how good you want it to perform on the edges. So that's the same effect as a telescope. The PSF is not the same everywhere. So that's another task is that sometimes you have to determine the PSF as a function of where it is on your spec. One special case is space telescope because for optical systems in space, the PSF is known extremely precisely. So this is the PSF of Day2 NARIT instrument at 12.8 micron. They can publish this and you can just download this and use it for your PSF photometry because it is known already extremely well even before launch from modeling the optical system. And after launch, they verify it and have published this PSF model. And the reason is because, of course, there's no atmosphere. So the only thing affecting the optics is just thermal expansion due to sunlight. And in case of Day2, this is very minimal. So yes, if you have space telescope data, PSF photometry is going to be the best thing to do. All right, before moving on to the calibration of photometry, do we have more questions about aperture and PSF photometry? You can also let this plane pass. All right, if not, okay, so now we have instrumental flux. We have a number that we get from our image. How do you turn this into a magnitude, or how do you turn this into a flux? So let's call this instrumental flux F. We define instrumental magnitude to simply be minus 2.5 log 10 of that flux. Of course, this magnitude will not mean anything. The number will be a little bit weird, but we can then convert this to a real magnitude from a real filter. And to do this, we compare our instrumental flux to a real flux of stars in our image. happen to have previously measured flux. This is kind of similar to absolute photometry. Once again, we use something that we use some stars that we have some information of prior in our image to try to do this calibration. A side note is that is not always possible. Sometimes you have really small field of view. Sometimes you have a very sparse area of the sky and you do not have any stars to do comparison with. In this case, you have to observe something called photometric standard stars, and these are stars with extremely well-known magnitudes in many, if not most bands. And you have to point your telescope at those stars and obtain observation. In those cases, the calibration is a little bit more complicated because you're not looking at the same part of the sky. You're looking through different patch of the atmosphere, and there are some corrections that you have to do. But that is kind of like so-called a primary calibration way. This way, it's simpler to execute, but it's not guaranteed. But in a lot of cases, observations we make these days are, the camera have big enough field of view to almost always have some stars with no magnitude. But that is something you should really check before you do. You find your observation is to make sure that you can do the photometric calibration afterwards. This practice of pointing the telescope to a different photometric star to do this photometric calibration is also the origin of the term. If you have heard photometric condition, when you do observation, photometric conditions mean that the transparency of your atmosphere is nearly constant to the point that you can move your telescope, look at a different star and move back, and then can use the observation of that star to calibrate your science. All right, so once we make sure we have that kind of star, we can do this measurement of a number called 0 point. And what this really means is that it's just the flux of something at magnitude 0. So going back to the definition we had before, the difference of magnitude, M1 minus M2, but in this case, M2 is just 0. So M, this equals to minus 2.5 log 10 of the instrumental flux divided by this 0 point magnitude, 0 point flux, sorry. And we just define this quantity 0 point magnitude to according to that equation. So yeah, it's essentially just like 2.5 log 10 of F0. So yes, to reiterate, for the flux calibration, we find a bunch of stars in our image that we know M, and we measure F, and then we solve this equation for the 0 point. The next side note is the magnitude. If magnitude scale is not confusing enough, there's also two different, or at least two commonly used standards for F0. How do we define a 0 point flux for the magnitude? Because if you recall that from definition, magnitude is just the difference between fluxes, right? So we have to set 0 somewhere. So there are two systems. One is called Vega magnitude system. In this system, we just define the star Vega in the constellation Lyra. If you've seen it in the summer, beautiful. Vega is at max 0 in all bands. So that's the Vega system. Whatever the flux of Vega is in that band, that is magnitude 0. This works actually quite well in the optical. Vega has a temperature of about 10,000 Kelvin, and a lot of things turn out to be 10,000 Kelvin. So when you have something at 10,000 Kelvin, then you get the same magnitude in all the bands. That's kind of the effect of the Vega system. When it does not work very well, it's in the infrared. And the reason is because Vega gets quite a lot fainter in the infrared. And then it actually has infrared access in addition to its kind of like a stellar emission. And the reason is because Vega, turns out, has some dust around it. This is something we did not know when this system came about, but now it's something we have to deal with. Is that the 0 point of Vega in the infrared is kind of like not very physical. So if your magnitudes are for filters, for like more classic filters, the UV-BRI, or even the near infrared JHK bands, those numbers are often in Vega magnitude, but you always have to check because it's not guaranteed. Like it all depends on who computes that magnitude and what system they use. In a different system called AB, I'm not actually sure what it stands for or why it's called AB. But in this system, 0 magnitude is defined as a specific flux of F nu. This system uses this like the frequency dependent version. F nu of this unit, 3631 Jansky. You can look up Jansky like has some weird definition, but it's commonly used in the radio and also in the infrared. This again, astronomers trying not to say 5 times 10 to the 20 to the minus 35 or something. Yes. And this is just Vega specific flux in the V band. So the magnitude in V band for AB and Vega are the same, and then they start to get further and further from each other, especially in the infrared. There's also a third system called ST magnitude. I have never seen it in a while. But in FT magnitude, instead of using F nu as a 0 point flux with F lambda. Right, and yes, most modern UGRIC photometry, the Sloan system, Pan-STAR photometry are in AB magnitude. And there's kind of like a, active, albeit very slow push in astronomy to try to get everything to be in AB magnitude. That way we never have to look at Vega magnitude ever again. Of course, as tradition in astronomy, we always never get rid of all things. So I just want to make sure that you are all aware of these two different systems. There are also a bunch of different photometric catalogs that you can look up. You don't need to go through this, but yeah, these are resources that you can use to try to get magnitude of things in your image. And in the exercise we will do after this, there's a package in AstroPi called Astro. Well, it's not in AstroPi, but it's a package called Astro Query that can also look up all of this information for you. So, as a summary, photometry is a science of measuring light. We can do it in 2 different ways. Aperture photometry, where we just define an aperture, sum everything up, and this is susceptible to image like issues with your image. There's also PSF photometry, where you say what the shape of the star looks like, and you come up with a function that you can fit to then integrate and get the flux out. For this hands-on, well, let's get to that after you come back. But any questions?
Sorry, I was just curious. If you want to convert from V magnitude, Vega magnitude to AB magnitude, or vice versa, how do you do that?
That's a great question. Can go back to. Yeah, you can use this very fundamental magnitude equation. So if M1 is is say Vega and M2 is AB magnitude, the difference is just you just divide the 0 point flux between the two systems. So F1 will be the 0 point for Vega in that band, and F2 will be 3631 cents. And this, in this case, F1, you have to go look up what the 0 point flux in that filter is. And again, this SPO website has a 0 point flux listed for all of the people. We're 10 minutes before break, so maybe we can break early and then reconvene for the next exercise. Okay, sounds good. Oh, let's go eat.